NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, everyone, and thank you for joining us for this May 2024 edition of the Von Karman series. My name is Marc Razze from JPL's Communications and Education Directorate, and it is my absolute pleasure to be your host today. But before we get to the rest of this, let me introduce our co-host today. Joining us for the Q&A portion of our show is Solar System Engagement and Networks Public Outreach Specialist, Mr. Laurance Fauconnet. Hi, Laurance.
Hey everyone, I'm excited to be here to handle the Q&A portion of our program tonight. Remember, this is your space program and we want you to be part of the conversation. So if you're watching on YouTube, X, or LinkedIn, please feel free to ask your questions in the chat box. Our social media team will be bringing in as many questions as we can throughout the evening. If you don't see the chat box, try reloading your page and it should pop up. We look forward to your questions. Back to you, Mark.
Thanks, Laurance. So folks, as you may already know, spaceflight is rather inherently risky. Amongst many things, it's freezing or boiling. Launches are a lot more violent than they might look from afar, and there's no air and the radiation is fairly prohibitive. And thus, testing is a pretty integral part of spacecraft development. It's probably clear we'd much rather break spacecraft things here on Earth, where we can fix them rather than out there in space where we can't. Today, we're going to talk about some of the ways we physically test our spacecraft, tests we endearingly refer to as shake and bake. Our guests today are specialists in this testing world. From the Environmental Thermal Test Group, we have Group Supervisor, Mr. Brad Kinter, and from the Environmental Dynamics Test and Instrumentation Group, we have Systems Test and Integration Engineer, Mr. Pete Landry. Hey, fellas, thanks for joining us today.
Hey, Mark, good to be here.
It's our pleasure. Thanks. We really appreciate your time, you guys. So, Pete, we're going to start with you. Here in the house, we often tend to refer to these tests as shake and bake, like I mentioned. But is it always, this is a question we've always had, is it always shake before bake?
Well, generally, we start with the shaking portion, yes, or even shock testing. What we want to do is get out of the way the most dangerous tests that might break the hardware, so that if we do need to do any redesign or any repairs, it can do that and then start the test campaign again to get qualified for launch.
Okay. So what, I guess really, what are you trying to learn, discover, kind of uncover when you're doing the vibe testing?
So for vibration testing, what we're trying to do is make sure that all the hardware that is developed and built here at JPL is going to survive launching on the rocket. It's a very violent event. There's a lot of shaking around and a lot of loud noises. And we want to simulate that here on Earth to make sure that when we do send it up, it doesn't break. Like you said, we want it to break, if it's going to, here on Earth, not up in space. Now, we don't break things very often. Mostly what we do is put them through the paces and qualify that they will survive, and then, certify that and send them on their way down to get other tests done. But, when things do malfunction, then we do have an opportunity to fix it and go on.
Okay. So what kind of machines do you guys use to do this kind of work? So
generally, we use a shaker. If you show slide number 1, this is a good example of a shaker. It's an electrodynamic shaker. It essentially operates like a big speaker. It's electromagnetic coils inside of there that are controlled with a controller that's fed through an amplifier that shakes that part that you see in that picture in particular, the part with all the holes. We would bolt down a part to that the plate with the holes, and then it would shake up and down and simulate the same shaking that it would see on the rocket during launch. That's our smallest shaker. It puts out about 400 pounds of force, so that's pushing and pulling up and down with about 400 pounds. So you can put something very small on that one. If you go to the next slide, number 2, that's a larger shaker. That's about 20,000 pounds force that can shake bigger components, boxes, cameras, that sort of thing, to make sure that they will survive inside the whole spacecraft when it gets sent up on the rocket. Now, once we get everything put together into a whole spacecraft or an instrument, something too large to go on that particular vibe table, we go to our large shaker, which you can see demonstrated on slide 3 in a little video. This one's testing the spherics, photon shields, which are shaken around, and you can see how they shake there during their test when this particular test hits the resonance of those different cones. So they're monitoring that and watching it to make sure that it doesn't shake itself apart down here on Earth, to make sure that when it does get sent up, it'll survive. And there's some engineers there on the scaffolding watching it to make sure everything looks good. One of them usually has a kill switch during the test, so if anything looks bad, they can kill the test from out there. And there's folks in a control room down the hall that are controlling the test to make sure that all the levels look good as prescribed by the test engineer.
All right, cool. What else do we have?
So after we do the vibration test, some things that are big and flat, like antennas and solar arrays, don't get really excited by a vibration test as much. They kind of wiggle around, but they don't shake as much. They'll be more excited by acoustic energy, the actual noise of the rocket. So we have an acoustic chamber, if you go to number 6, where we basically simulate the sound that the rocket will make. And what we're mainly looking from there is testing big reflectors, big spacecraft body panels. You can see a lot of flat surfaces there. And we actually have big horns that are fed with nitrogen through noisemakers. You can see the exit from one of the horns there in the top center, that black square is the inlet into the chamber from one of the horns that produces all this noise that basically makes the spacecraft experience the same thing it would do sitting on top of the rocket riding into space. We have sensors on the spacecraft, mostly accelerometers, that will measure the vibrations and make sure that everything is okay to pack it up and send it on to the rocket to actually be launched. So that test chamber is a big concrete box, basically, that reflects all of the acoustic energy back inside, and it's controlled by microphones. There's a computer that controls the noise going into the chamber, and then it listens with all of these microphones to make sure that it's producing the correct sound. So you see those black sticks, they're booms, sticking microphones in different areas of the chamber to make sure that all the spots around the spacecraft are hearing the right sound that it would hear when it's going up on the rocket. So that's kind of usually the last stop we do in dynamics before we kind of check all the boxes and send it off that it's good.
And that's one of those tests you can like hear from outside the building, right?
Oh yeah, yeah. You know, I used to have an office on the other side of the building, and when they'd run the acoustic chamber, I could still hear it. It sounded like a jet flying around outside or something. But it was even through big, thick concrete walls, it still does get very loud.
Yeah, those are some monster air horns in there. I think we missed one, though, about the shock testing. I know you mentioned it, and let's go back and revisit that for a second.
So if you go to slide 4, one of the other types of testing we do is shock testing. Now, this isn't mostly to simulate liftoff as it is to simulate some of the devices that are used to deploy or release different mechanisms on spacecraft. They usually fire a little pyrotechnic device, and those devices can put a big shock into the system, like hitting it with a hammer in a certain area. These are characterized before the things are built, and then they'll take that simulated shock and replicate it on this machine that we've got. They call it a tunable beam. It's basically a big flat beam that's clamped at the ends, and then we have a big air cannon that fires a metal slug up into it and hits it, like hitting it with a big hammer. And then it will ring in certain ways, and we can change parameters to make it ring just like the pyro device would make it ring up on the spacecraft when it's going through a deployment or another action that would cause it to see shock. So we can mount different hardware to the beam, hit it, and then take measurements, make sure it hits the right levels, and then qualify it for those pyrotechnic events when it gets out into space. If you look at number 5, you'll see a little video of a piece of hardware getting tested. You can see once that thing gets hit, all those different components jiggle around in place and can possibly be damaged by that event. So we have to make sure that it survives before and after and sees the right expected levels that we would normally see. This test is measured in the thousands of Gs. So we're actually measuring thousands of Gs of shock when it goes through here. Now, this is a very short duration, very high frequency, so we're not, pushing it into the bench or anything like you would feel G's pushing you back in your car when you accelerate onto the freeway. But the sensors, the accelerometers that we have on here, will measure in the thousands of Gs. For vibration and acoustic, we're measuring maybe the tens of Gs. We're talking a test of about 10 to 20 Gs, but over a longer duration of time.
Wow, that piece is getting clobbered.
Yeah, it's you can see some little particles flying up from the bottom there too. It's a pretty violent hit.
It's a scientific term there, clobbered.
Yeah.
Sorry, folks. So you must have some pretty good stories from some of these tests. Anything you can share with us?
It's funny. When we do testing, it's usually really tense. It's real high tension. Everybody's kind of on edge because you don't know what's going to happen, if the part's going to pass or fail, if something's going to break, how long things are going to take. So a lot of tests will come up and they'll have some kind of, one test came up, they had like a celebratory song they'd play after every axis was finished. Or one would do videos of them like dancing outside. They had a different dance they would do after every axis was finished. We'll do 3 axes of testing whenever we test a piece of hardware, X, Y, and Z, to make sure that it survives shaking in all the different axes. So every one we get to check off is another sigh of relief that this thing is going to survive on its way to space.
That's great. I'm sure there are a few superstitions or traditions that go on up there as well. All right, so let's check on our audience. Laurance, do we have any questions for Pete?
Yeah, we have some great questions coming in. Matthew Hansen from YouTube asks, how long before the launch will the shake and bake take? When does it take place?
That's an excellent question. We start testing parts as they're made. So as parts will start to get made for spacecraft, from tiny circuit boards up to assemblies like electronics boxes, amplifiers, that sort of thing, mechanisms, and then up to instruments, and then of course up to the whole spacecraft. So we kind of see the assembly of the parts from the beginning to the end. Now the big spacecraft test is usually right before they pack it up and send it off to the rocket to be launched. And Brad can talk a little bit more about that too. But we're kind of the last stop before they pack it up. So Europa Clipper, our most recent mission, tested with us a few months ago and with Brad recently, and now they're packing it up to go ship it to Florida to be launched. So we're a lot of times kind of one of the first and the last stops for projects as they come through.
And Annie on LinkedIn asks, if the atmosphere is dense and gravity is low, how would that affect the descent of the spacecraft? What type of vibration test do you do for that?
That's another good question. We typically test to make sure things will survive liftoff on a rocket. But when you have different events that a spacecraft might go through, like the rovers going through EDL on the way down to the surface of Mars, they'll come and test for that as well. We had an EDL profile that we would run through the shaker on rover parts to make sure that it would survive that entry into the Martian atmosphere, because there was a different type of shaking that would go on there. You don't have a rocket burning and shaking and exploding, but you have the resistance from the atmosphere as it's going through. So we had an EDL profile that we would actually run on those different things, and it depends on what simulations will tell them what levels should be run, as well as maybe measurements that were taken on previous missions. So a previous rover that entered into the Martian atmosphere could have had an accelerometer on board that actually measured those levels, and we use those same levels to test the next mission to make sure it'll survive the same event.
And Child Car on YouTube asks, how has the shake and bake tests evolved over the years?
I'll let Brad talk a little more to this one too, because his facility that he'll get into is pretty old. Our stuff is fairly new, but the more things become automated, more things become computer controlled, less knobs and more computer clicks, that sort of thing. Our whole tests are mostly computer controlled now, with the computer calculating the spectrum that goes out to the shaker to shake these parts. Back in the old days, before my time, things, the equipment took up the whole room that would run these tests and record all the data and everything, and it would take hours to process. Whereas now we can run and record a test from a desk and process data in minutes of hundreds of channels rather than a day for less than 100 channels. So things get faster, more powerful, and a little more streamlined with computers involved.
Okay, thank you. Back to you, Mark.
Thanks. Good job, gentlemen. So, Brad, let's get you back into this show, shall we? So, as we've talked about already, we do call it shake and bake, but your specialty is bake, right? And it's actually a lot more than that, right?
Yeah, that's right, Mark. It is actually a lot more than bake. So bake typically refers to bake outs, where we're subjecting hardware to high temperatures under vacuum in order to essentially clean the parts. So under vacuum, molecules will want to be released. So what we're trying to do is heat up components that might be otherwise dirty and expose other pieces of hardware to those contaminants. And we're trying to remove them ahead of time. But really, we're doing a lot more than that. We're trying to actually simulate space for many of the parts, and that's what we're really trying to get down to. And so slide number 7, please. We start with these chambers of relatively small size, and we work our way up. And so we're simulating space in these chambers that are anywhere from 2 to 25 feet, like the chamber you see behind me, which is our 25-foot space simulator. And they all basically use the same principles across. Slide number 8, please. And that is, we're first trying to simulate space by removing the atmosphere, just like space would be. And so we're pumping out all of the air that's in there, not all of the air, but most of the air. In fact, we're getting down to pressure levels that are 1/billionth of the air that we breathe here. And so what that's doing is that's getting rid of one of the strongest heat transfer mechanisms, which is convection. And what that's leaving is only radiation or conductive heat transfer. And then the other thing we're doing is we're subjecting the hardware to different boundary temperatures, just like they would see in space. So in space, you have just this absolute cold, freezing cold, down to absolute zero of the deep body of space on one side. And then you sometimes have a large heat source like the sun on the other. And so in this picture, in this slide, if we go look at this slide, you can see this black envelope around this hardware that's sitting in between. And those are the thermal shrouds. And those thermal shrouds we're able to control with gaseous and liquid nitrogen from temperatures anywhere as high as plus 120 degrees centigrade all the way down to minus 185 degrees centigrade using liquid nitrogen in that case. And then in some cases, if we go to slide 9, we also want to simulate hot sources. So such as the sun, we can use things like either heated shrouds, or we can also use xenon arc lamps, such as this single xenon arc lamp, which is shining in through a chamber window and hitting a surface on the hardware. And then as we progress with these components, let's go to slide 10. We basically work our way up in size. So these smaller pieces get built into bigger ones and bigger ones and bigger ones. And, these little electronics and whatnot are now getting integrated into full-blown instruments. And those obviously take up more size. And as a result, we need bigger chambers. So in this picture, we have our 10-foot chamber, which is testing an instrument. And again, the principles are all the same. You can see the very large shroud that's enveloping the actual chamber walls, and the chamber vessel more or less looks the same. It's just upscaled. And then finally, going to slide 11, if the hardware is big enough, we need the 25-foot space simulator. And here you can see Europa Clipper getting recently installed and tested. And again, this is all to prove out all of these components that are coming together and being built up as a spacecraft so that we can thoroughly test it and make sure that it can survive from a thermal standpoint, the longevity of a mission in space.
And that 25-footer is certainly not your average chamber, right? I've been up there a few times, and it's pretty spectacular.
No, I mean, the size gives it away. 25-foot working diameter inside, and it's certainly the largest at JPL. And it does have a long history going back to the space race. So it was originally built in 1961 with a focus on interplanetary space simulation. And as a result, they needed solar to be part of that. And that's one of the things that makes this particular facility unique, is that it has solar simulation capabilities, even at the 25-foot level. And so going on to slide 12, please. You can see back in the day when this thing was starting to be constructed, it was literally looks like a chamber just thrust into the ground there. And then slide 13, the chamber's so big that they actually then had to build the walls around it. And then moving on to slide 14, in 1967, there was a major modification to alter the solar simulator into the current version that we have today. And so here is the 23-foot diameter collimating mirror getting loaded inside of the front chamber door. That's the same chamber door you saw in the Clipper picture where the spacecraft gets loaded. And so at the final specs that we arrived at with this final build in 1967 is that the chamber is 25 feet in diameter and 85 feet high. So it's roughly 50,000 cubic feet of volume. And to work with that incredible size, we need a whole host of roughing pumps, vacuum pumps, 10 cryo pumps, and shrouds from top to bottom. So it's pretty impressive.
Yeah, give us, if you could, a little more, like a few nuts and bolts about how this thing actually works and how cold can it actually get?
Well, first let's start with how the chamber actually seals, because I haven't shown you the door yet. And so moving on to the next slide here, we can actually see this is a 25-ton piece of wall that is our chamber door that moves over on rails and then gets pushed forward into the actual chamber side. So that's how we actually seal. And then once we seal, now we can actually start to pump down. And then once we pump down, that's when we can actually start changing our temperatures, going hot, going cold. So again, we're going anywhere from minus 185 degrees centigrade using liquid nitrogen, or we can use gaseous nitrogen for any temperatures above that up to about plus 100 degrees centigrade.
That's got to be a lot of liquid nitrogen going through that chamber.
Yes, it certainly is. Just in the piping alone inside of the chamber is 6,000 gallons worth of liquid once it gets pumped in. And we can sometimes burn it at a rate of 3,000 gallons per hour just to cool down, which is the equivalent of about a truck every 2 hours.
That's a lot of liquid nitrogen. We've still seen that's why they're lined up on Oak Grove now and then, right?
Yes, absolutely right.
So you mentioned that solar simulation capability. And I understand our chamber is fairly unique. Tell us more about that.
Sure. So if we go to slide 16, here we can see a side cutout view of the chamber itself and the solar simulator. The lamps that illuminate are xenon arc lamps. And so they're pressurized xenon inside of these bulbs. And there's 37 of them down 3 floors below in the basement. So in that graphic, you can see the little person standing down there to represent scale. And down there are the lamps. They shine up onto an integrating lens. That light then passes all the way up onto that 23-foot diameter mirror, which is at the ceiling of the chamber. And then that light is then collimated and sent down to the spacecraft below.
Cool. You have any pictures of that? I think we have some shots of the lamps.
Yeah, so if we go to shot 17, you can see Europa Clipper being bathed in the artificial sunlight.
Oh, cool.
So there we have it suspended inside the chamber, and it's hanging above the lower floor shroud that you can see real nice there in black. And then slide 18, we can get kind of a better feel of the lamps themselves. Those are some of the bulbs. You can see about 3 bulbs in a row there sitting inside of the reflectors. And those are what's putting out that intense light source, which is then hitting the lens above. And then slide 19, you can kind of get a bigger picture looking down onto all 37 lamps. There we have, roughly 20 of them illuminated for one of our previous tests. So all total, when all lamps are running at 32 kilowatts, that's about 1 megawatt of power, which is an incredible amount of electricity that's running through this.
That's 32,000 watts a bulb.
Yep.
That's nuts. But you got to do it. So, yeah, very cool. Do you have any, I'm going to ask you the same question I asked Pete. You have any fun stories?
Yeah, we did. One of the fairly recent ones was when we were testing NISAR, we suddenly developed a leak through the chamber door when we started going cold. And once we identified where the leak path was, we realized the only way to seal it and save the test was to use about 20 C-clamps around the perimeter of the door to hold it closed. So that's what saved our test from having to abort and return and fix the problem.
Yeah, I can imagine. How long does it take to pump the chamber down?
It can take anywhere from about 90 minutes or maybe a few hours, depending on the sensitivity of the hardware inside. Some like to pump fast. Some don't want to stir things up, so they want to kind of take it easy.
That makes sense. You were telling me a story about the cloud that forms in the chamber.
Yeah, that's right. So sometimes we pump down a little too fast using some of the other compressors, and so we're actually able to pass below the dew point of the air inside, and so you'll get a sudden cloud formation. Now, typically spacecraft don't like that, so we try to avoid pumping down at that rate. But one other incredible fact is just how much air we're removing in this process, and that ends up making the chamber about 3,000 pounds lighter based on the amount of air we're removing.
That's crazy. That's neat. Okay, let's go for some Q&A. Laurance, do we have any questions we can throw at Brad?
Absolutely. The Opal Guy on YouTube asks, so what happens if the equipment exceeds the capacity of the 20-foot chamber?
In that case, then the customer will usually have to move to a chamber that can accommodate it. So when the chamber was built, it was built around the fairing size at the time that really shouldn't need to be exceeded. But we are starting to push the limits. So in that case, we can't just easily grow the chamber size. So it's a matter of planning for either building our own chamber here at Lab or using resources that are available in the outside world right now.
Thank you. And Matthew Henson on YouTube asks, and I'm going to paraphrase this a little bit, but or did the instruments on Europa Clipper work in the chamber during testing?
Yes, as far as I know, they worked. I'm sure that they found some things that they wanted to tweak as a result of the testing. Almost no test goes perfect, where they say, we're going to just send it up into space as is. There's almost always some blanket modifications, something got too hot, too cold to be comfortable, all sorts of things. So I think for the most part, everything went pretty smooth, but I'm sure, like I said, that they chose to tweak something.
Thank you. And Fly with Cian on YouTube asks, what are some of the different spacecraft that you have seen go through Shake and Bake that have gone through testing?
Oh boy, it's been a lot. So I've seen MSL, M2020 Perseverance, and the cruise stage. One of the helicopters, the helicopters was pretty exciting to test in that environment. NISAR, SWAT, Clipper, Psyche. So we've seen a lot come through here, and that's just in my time. And again, this place has existed for 60 plus years. So there's been a lot that's come through here.
Cool. And now I have some questions that could work for both you and for Pete. So Donald Miller on YouTube asks, do you have examples of parts that needed multiple cycles of testing for improving or retesting?
Yeah, certainly parts have come through that have had to undergo rework, especially with things coming apart, like from CTE, mismatch of materials moving against each other under thermal conditions tends to really tweak things. And so there's definitely been those examples that have come through here where they've had to kind of go back to the drawing board essentially and say, what can we do to prevent this from happening?
Yeah, on our end, the same thing happens if usually it's small components inside. You might have a failure of an electronic part or a mechanism. The most fun is usually when we're doing a shake test, and the vibrations will actually cause screws to back out sometimes, so they have to go put a little like Loctite on it to make it stay in, or use a different type of screw that won't back out at the certain vibration frequencies. And usually that's when the engineers will be watching it and hit the kill switch to stop the test, or they can even see it from our post-test analysis after the fact and figure out that, yeah, something around here is a little loose.
Got it. And just one more question, and maybe Pete, we can start with you. But what kind of degree do you need to get into this type of work? This was asked by Zilberstein on YouTube. Maybe you can talk a little bit about your journey to how you got here.
My journey, actually, when I was in college, I was actually an intern here at JPL doing engineering, and I actually worked with Marc doing tours as an intern, getting to see all the corners of the lab and learning a lot about it. And knew I really wanted to work here. So once I got towards graduation, I was looking for different jobs and ended up being an opening up at the environmental test lab. And I really, I had a degree in engineering with a focus on mechanical engineering, and came in as an instrumentation engineer. So I was in charge of taking all of the measurements from dynamic tests, from these shock and acoustic and vibration tests, and didn't really even know much about instrumentation, but was very eager to learn. And over the past several years, I've really learned a lot about testing and instrumentation and recording systems and all this other stuff. So, just because I studied mostly mechanical engineering in college doesn't mean, that I necessarily went there. And there's a lot of stories of engineers that have kind of deviated from their main focus in school to find themselves in a career that they actually really like.
Brad, what about you?
So my start was interesting. I was working at a juice bar in high school, about to start my program at Cal Poly Pomona for mechanical engineering, when my manager told me that her husband had a position for an internship opened up at JPL. And at the time, I had no clue what JPL even was. I wasn't even sure that I wanted to do mechanical engineering. But once I started working here, I absolutely fell in love with the place. I kind of moved around different jobs here at JPL until I finally found that I really loved environmental testing. And so that's when I got into my role here. So the journey definitely wasn't straightforward, but it was definitely well worth it in the long run. And I'm so glad to have stuck with that.
Thank you. All right, back to you, Marc.
Thanks so much, Laurance. Just one other thing to go on to what Pete had mentioned. Our internship program, folks, they're very good. They're competitive, as you would imagine, but there's a lot more information about those programs on our website. So anybody watching, if you're interested, there's a ton of information on the site, jpl.nasa.gov. So given that, that's about all the time I guess we have this evening. So let me thank Brad, Pete, for being our guest today. Thank you so much for helping put this together. Laurance, the social media team, thank you so much for handling all those questions. Of course, none of this could happen without our crack audiovisual team, so thanks all of you folks behind the scenes for that. And then, of course, finally, let me thank all of you for tuning in. As we've said before, this is, in fact, your space program, and we're grateful that you're interested and involved. Please tune in next month when we'll talk about NASA spin-offs. And in the meantime, folks, stay well and stay curious. Good night.